Okay, this is a review for the final exam. It's slightly different from the previous exams in that the other 90-minute exams you've had 4 hours. Because of back-to-back exams, this has to be 1 hour and 50 minutes, 110 minutes, and you have to vacate the room after that. So it's slightly different in terms of length, and of course the questions accommodate that difference as well. As in all exams, I think you know how to take exams. You should look amongst the 3 questions to see which ones might be easier and do those first, of course, etc. The topical areas, it's supposed to be comprehensive, but actually in reality it's the final portions of the class, which include pipe flow networks, which mean that you need to know something about pipe flow behavior, which is week 10. External flows, section 12.1 to 12.3, and open channel flows. So those are the 3 topical areas. The 3 questions, one is a pipe flow network according to week 11, an external flow question according to the material for week 12, and also open channel flows according to week 13. And so as in the previous reviews, this will be online and you should look at it. You should look at the other materials that are available. But what I'll try and do, at least today, is to talk about the minimum set of expressions you need. And if you know how to use them, then you probably will behave fair well within the test. Okay. So the first question area is pipe flow networks. And so this builds on the material from Bernoulli. We spent some time talking about Bernoulli. You know the equations probably quite well. You know that when we use Bernoulli in the energy equation, the material, I guess, from week 8, that we have to write behaviors upstream and downstream. So we have to be cognizant of the fact that we have to go from upstream to downstream. That we can have energy added into the system by a pump, and also pump or head losses within the system. And our Bernoulli equation is written in a standard way. If you write it in terms that include length, then it's the elevation, pressure, and velocity heads with a component that represents the pump within the system, and that has to be equal to the downstream components of elevation, pressure, and velocity head, plus the sum of losses that occur from both minor and major components. Minor being bends, etc., major being the slow but ultimately large changes in head that result from pipe flow losses. And so the pump head is always positive if it's a pump. It's negative if it's a turbine. And we can always convert the magnitudes of the pump head to the power of the pump in watts divided by the mass flow rate times G. That's always the case. And if it's a turbine taking energy out of the system, it just ends up being as a negative term in this. And the head losses within the system come in 2 forms. They come in pipe losses, if you like, where the head losses are the summation of a friction factor, a length to diameter ratio, and the velocity squared over 2g term that's present within the pipe, not at the ends, but actually within the pipe of interest. And also in terms of the Darcy-Weisbach equation, which is a head loss, which is typically a loss coefficient multiplied again by v squared over 2g, where this is the velocity within that fitting, so to speak. And so the reality of both of these behaviors are that if you look at the losses, we can think of it in terms of a Moody diagram, if you like, with two behaviors apparent within it: a friction factor, a Reynolds number, which is a velocity, a diameter, or a characteristic dimension, and density of the flowing fluid divided by viscosity, and divided by this transition from laminar to turbulent, and as you go across this boundary. And importantly, the behaviors that you have within here, that in the laminar regime, the friction factor is proportional to Reynolds number. If it's a circular tube, it's something like this. And in the region beyond that, these individual contours are lines of roughness divided by pump diameter. And importantly, it means that the friction factor is constant as you get above some critical Reynolds number. And so if you double the flow velocity, the magnitude of the friction factor doesn't change. And so in using that in this expression here, the dependency, I guess, of the velocity of the friction factor ends up being a square term. One of the velocities gets cancelled out if you use Reynolds number. And so the forms of solving the equations to do that change. So this is important. And of course, this is the same behavior that we'll probably, well, not probably, we'll talk about also in terms of external flows. And that is that if you look at Reynolds number versus drag coefficient or lift coefficient, then you see similar behaviors that end up being constant or nearly constant within the region above some particular value of Reynolds number. Again, same order of magnitude, 2000 or so, where depending on the characteristic dimension that's used. If we look at networks, then networks come in two flavors. They come in the behavior when you have an upstream tank and a downstream tank communicating with each other, in which case, if you look at the flow between these two different levels, where there's some delta Z across here, then in those particular cases, the head loss in each of the pipes are constant. They have to be the same for this pipe and for this pipe. And the flow rates for the total system have to equal to the sum of the individual flow rates in each of the individual pipes. And so for parallel flows, this is the relationship that we deal with. And for flows which are segmented, in pipes of different diameters as they go upstream, from a pressure 1 here to a pressure 2 here, then the flow within each of these components, Q1, Q2, etc., have to be the same. And the head losses that result along this have to be the sum of the individual head losses on each of the individual components. And so physically, a parallel network versus a series network are physically different from each other, and we have to accommodate from in that way. Okay, so that's pipes and pipe networks, and so if you know those expressions, that should be enough for you to thrive in that particular case. If we look at external flows, then if you look at forces that may be applied on a body, due to drag or due to lift. They result from the flow around that body, which has some velocity some distance away from it. Quite straightforwardly, the coefficient of drag is equal to some drag force divided by rho v squared a. This is, if you like, this is an Euler number, a force divided by density v squared over a. This a would typically be the what's called the planiform area. And so that means that it would be the frontal area that this sphere, in this particular case, looks on. So it's pi d squared upon 4 would be the area that would be used. Or if it was an aircraft wing, it would be typically the area of that wing. Density of the flowing fluid, the far field velocity, and this is the magnitude, I guess if we're calling it FD, this is the magnitude of the force that's applied. By definition, these terms top and bottom cancel out, so they're dimensionless, and a similar expression exists for the coefficient of lift, that this is the force due to lift, again, rho v squared over some appropriate area in the system. We made the case before that the geometries that relate to this are essentially geometries like this, which vary at low Reynolds numbers. They are laminar, and the coefficient of drag or the coefficient of lift is some function of typically 1 over Reynolds number. And above that magnitude, they are independent of Reynolds number, and the magnitude of the coefficient of drag or lift is constant. And so that changes the way in which you solve equations, because typically you substitute a magnitude of that constant, which is either a constant or a function of the Reynolds number, into this expression, and then you end up solving it to calculate, well, I guess actually it would be this, right? This would be the magnitude of the coefficient of drag or lift, and you'd solve it for the force that's applied. So for instance, if you have a system where you have as we talked in class, have a water tower which has air flowing past it, and you want to know what the force is that is applied on this water tower, then you can use this directly if you know the magnitude of the coefficient of drift. If you know the velocity and you know the area and density, you can calculate what the force is that would be applied. And in the normal way, if you're looking at the failure modes of these systems, you're looking either at the sum of the forces in the x direction equals 0, the sum of the forces in the y direction are equal to 0, or the sum of the moments are equal to 0. Moments about some failing location. And so if you do that, then you have enough information to be able to typically show, calculate, for instance, what is the velocity that might be large enough to cause this to fail. All right? So those are external flows. And the final component would be some discussion on open channel flows. And we have uniform flows, we have gradually varying flows and rapidly varying flows. If you look at uniform flows, then those are the Chézy formula. Which allows you to calculate flows within straightforward channel shapes. Of some width and some height, for instance, or some different shape attached to that. And they give us the velocity, average velocity of flow as a function of some coefficient, which is 1 for SI, a Manning's number, the hydraulic radius of the channel to the power 2/3 multiplied by the slope of the base of the channel to the power 1/2. So this slope of the base of the channel is this angle here, this angle. S0 is equal to a height multiplied by a length. So L times Y. And by definition, the hydraulic radius is equal to the area of flow, which in this case would just be equal to W times H, divided by the perimeter, which is just equal to 2H plus W, the wetted perimeter, which would be this length here, plus this length here, plus this length here on the bottom, and as opposed to the total area here, which is this magnitude here. If you want to know what the volumetric flow rate is, it's just equal to the velocity times the cross-sectional area, which in terms of this is again this coefficient, which is 1 for SI, Manning number, the area, hydraulic radius to the 2/3, and the slope of the base of the channel as it goes downstream. These behaviors are actually very similar, of course, to the behavior for both the external flows and pipe flows. And so if you look at the magnitudes of the Manning's number versus Reynolds number, then you have this change in behavior for some critical hydraulic radius. And the behaviors are that in the laminar regime, you have some behavior like this, and in the turbulent regime, you have different numbers of Manning's number, which would be these individual components here. And so the reason is that we use Manning's numbers are that typically for flow in open channels, we're at magnitudes which are in the turbulent regime. And so there's a single magnitude that defines behavior for a particular kind of lining of the channel, and that defines a single number which goes into here to be able to calculate the given flow rate. If you need to calculate magnitudes for composite channels, which we also talked about, then you just need to divide it up in some way into individual components, whereby you can look at the individual flows within individual portions of the channel. So you can look at the flow in this as a function of the hydraulic radius given by this, which would just be this magnitude here. The hydraulic radius would just be this length here, and the area would be this area here. You don't include this magnitude here because this, of course, is water, and it's moving at the same speed as the block next door to it. So when you calculate the hydraulic radius for a composite channel, you should sum it for the individual components, not including the parts which are water that divide them between them. And that's about it, I think, in terms of things. So certainly with these expressions that we talked about here, you certainly have everything you need to perform well, and indeed to thrive on the final. And I wish you the very best on it. Okay, take care. Good luck.